Welcome back to the third talk of this afternoon. We're very happy to have Felix Schlenk from Université de Neuchâtel, who will tell us about symplectically knotted cubes.
Thank you very much, Soban, and also Alex and Vincent and everybody who had a great week here in Paris so far. And unfortunately, it's over tomorrow, but also to the organizers of the Paris, Princeton, Tel-Aviv seminar. It's a real honor to speak here, and not so easy to speak after Leonid. I will only bring you some numbers. So the topic is somehow simple, and I will spend some time first with putting it into context, even though you may know that very well, and then come to the numbers. You will see I like numbers. So this is joint work with Joey Brendel and Christian Michalkin, and there, of course, ideas of many other people. We'll see. So it's about symplectic embeddings. Maybe I should make that bigger. So I will first ask 3 questions in this field and then say what is known in which, and then come to the things we are working on now and what is open and what is not. So the problem is that you have a domain. Let's take a domain as simple as you like in standard symplectic space, and you may fix 4-dimensional things if you like with the standard symplectic form and think of it easy. The boundary may not be smooth, but take something convex or a polydisk or an ellipsoid or a disjoint union of such things, and you take also a target symplectic manifold. And since the domain is connected, I want it to be connected. And I look at the space of all symplectic embeddings of the domain into this fixed target. Okay? So there are essentially 3 questions you can ask. The first one is, you want to understand whether this space is empty or not. Only then the other questions make sense. Once you have checked it is not empty, you could try to understand the structure of the space. The first one would certainly be to understand whether it's connected or not. And there are variations of connectivity, and I will come to this. So essentially, it means to understand the pi0 of this space. And then once you have maybe understood that, you can ask for the full homotopy type, or maybe a bit easier, the pi k or the hk or something like this. So of course, it's a kind of an obvious sequence of questions you want to ask. And what we know about these questions is extremely different. So about, I would say here there are maybe 100 papers, and here there are about 3 or 4, and here probably 2. And I will now describe this. So on question 1, very, very much is known, right? So this is, I give you some examples, and then you see that, of course, this is also the birthplace of the symplectic rigidity phenomenon, which can be formulated in many ways, but in Lagrangian submanifolds, but in particular by embedding problems. And the camel problem is one, and Chromosome squeezing problem is one. So we have here parameters, and for certain A and big A, the embedding exists, and for certain not. Then you can refine this question, and already Gromov started this. You can take here this joint union of balls, let's say of dimension 4, to fix the ideas, and you can take them of equal size or not, and you give you a target manifold, and you ask whether you can embed or not. Usually these questions are formulated a bit differently. You ask for the biggest size here, so that, or you ask for the smallest size here, so that K disjoint balls embed, and then gives you in a sequence of numbers parameterized by K. And this was already started by Gromov, and then by Dusa and Leonid, and by Paul Biran. And then together with work of Lee and Liu, this question is fully answered. So the symplectic embedding problem that asks for an embedding of finitely many balls of size HA, of variable size, into the smallest target ball you can ask for, is completely solved. And it's quite a long and beautiful story that uses a lot of machinery, in particular cybergrid and ideas, geometric ideas like inflation. So this is quite a long story. And then instead of balls, you can also ask for ellipsoid embeddings. It's related because an ellipsoid can be seen as a disjoint union of balls glued together. And here you have now a family problem, so a full real parameter, and the smallest a such that for a given small a, such an embedding exists is also known. And this leads to these staircases and something like the fine structure of symplectic rigidity. And from here on, many works have been undertaken, and the results are really, for instance, just last week, I saw a work by McDuff and Nikki McGill. So they found here is one staircase, and they put a parameter in the target set, namely a certain blow up of CP2. And the size of the blow up gives you here in target a second parameter. And they find like a fractal set of B where they find this fine structure. So also Mike Usher had similar work where the answer is extremely complicated. So to be short on this question one, there are many results, and in each new result you generate, of course, 3 more. So it's kind of exploding, and much is known and much is unknown, and many new questions are generated. But the question whether these sets are connected or not is much less understood. And I come to this in the whole rest of the talk. But the last question, to understand the full homotopy type, is almost unexplored. So here I know only 2 works, the ones by Agnos and Lalonde, and the one by Lalonde and Pincenot first. So these authors, they studied the homotopy type of the space of symplectic embeddings of a fixed ball into a product of spheres. And the spheres, here you fix maybe the size to be 1, and here the size to be big A. And as a function of A, you fix also here a size. And as a function of A, you try to understand the space of symplectic embeddings of this space. And the answer again is rather breathtaking. So this space has not the homotopy type of a countable CW complex. It's extremely rich, this space. This is almost the only thing. The other work that was done about 2 years ago by Gaides and Munteanu is about higher homology groups. So maybe I also sketch this briefly. So they look at certain ellipsoids of arbitrary dimension, but let's think of it maybe 4-dimensional. They take a target and just an embedded ellipsoid that should be a bit different, but it should not be too round. So this should be less, and this should be more than half of this. You know what I mean? I mean areas of shadows. And you ask for the structure of the space of embeddings of this smaller one into this bigger ellipsoid. And there are certain parameters. And what they do is, you see on this first ellipsoid, this is the outer one, and this is the inner one. And on the inner one, of course, it has parameters A, B. The 2 torus acts just by turning circle-wise symplectically in the coordinates. So what they prove is that under good assumptions on the sizes of the inner ellipsoid and the outer, the action of T2 you have is injective in cohomology. So in cohomology, the action, so you have for every element of the 2 torus, and coefficients are Z, not 2Z, you get a map, and then you get an inclusion into the symplectic embedding space of this smaller ellipsoid into this bigger, and this is injective. So here you have higher homotopy groups that inject. So I wish to stress that under these maps, the inner ellipsoid is as a set, unchanged. You only operate on the set, you don't really act as a set, but they are maps and they form circles, and these circles are not contractible. They are homologically injective, okay? Because when you look at pi 1, at pi 0, you can look at different equivalence relations. So here, the embeddings do not change the set, but you can turn, and these, well, you have quite a lot of topology given by the inclusion here from the homology. So I didn't write it well, but I should say that the map of homology into the homology of the symplectomorphism of the set of symplectic embeddings of E into E prime is injective. That's the result. And more is not known about higher homotopy groups or homology groups. So now I come to our question, question 2. I want to study the set of components of the space of symplectic embeddings. I want to know when I have two, can I move one to the other, right? Okay, so here I should be a bit more precise because when you are not, you prove different wrong things and different things. So what does symplectic embedding mean? I always take a closed compact domain. It may be more natural to take something open because then it's clear what smooth means, but this is actually very awkward. If the domain is open, then at the boundary, very bad things can happen and then you don't really know what to do and it's hard to prove something reasonable. So the domain is always compact here and think of it simply connected. And then symplectic embedding just means that you can actually embed a bit more, an open set containing that compact set. And that's the definition of what I mean. And then this embedding space has some topology. You can take C infinity. That's fine. It's not important. So here I want to speak of components, and you can define several equivalence relations here. It's a little bit a technical discussion, but it's maybe worthwhile because it leads really to different results and one should say what one does. Okay, I now look always at embeddings of such a set K that you should take simply connected and maybe star-shaped, maybe smooth boundary, maybe a polydisk. More I will not do. And I look at these embeddings into M. And the, of course, strictest relation you can think of is to say that you can move one through to the other. Because if K is connected, if K is simply connected, this is really exactly the same as to say that there is an ambient Hamiltonian isotopy of M that moves as a map, not as a set, the first embedding to the second, right? So this is the strictest, finest relation you can define. You can compose the first map with an ambient Hamiltonian isotopy. At least this is the same if K is simply connected with the second. Another relation would be that you find a compactly supported or not compactly supported symplectomorphism of outer space that brings the first map to the second. So they are really maps, and these two relations in general are not the same, of course, but sometimes they are. I will come to that. But then there is a rougher one, namely that you only say that the images of the sets are mapped one to the other. Yes?
You ask that stylish isotopic by
No, I don't ask for that. I just want a symplectomorph. Just want a compactly supported symplectomorphism of ambient space that corrects the first map to the second as a map. In general, is of course the big difference. The point is, in those cases where this problem is a bit understood, M is such that the mapping class group is trivial, and then they become the same. And there is also no flux because the image is simply connected. So I will come to that. It's true that in general, these two relations are very different, but in all cases where something is known, they're actually the same. It's just because we don't know so much. The target spaces that are understood are something like CP2 or S2 cross S2 or star-shaped domains in R4. And there is no mapping class group by Gromov and no topology. Okay. And the roughest, or among the roughest relations, is that you just map the set by the correction map to the other as a set. So this has been looked at by Jean Gutt and Mike Usher. They actually not even have this compactly supported. This is really the roughest you can imagine. And they call this knotted. But I need compactly supported. I will study this relation. And this is probably quite more general than these. So you see here, you may have many more islands in Pi-C in many more different equivalence classes than here. They could really fuse. Okay, so I wish well, it's clear that this is clear. The first one is the finest and the last one, the roughest. So as a picture is like this. When you have these two, you can either try to move it through Hamiltonianly, or you can try to find an automorphism of M that relates these two maps, or you can just try to map the red set as a set to the blue set as a set. Sorry for this technicality. And I mostly look at the last one. Okay, and the remark that answers your question, hopefully, is that if the target manifold is like star-shaped in R4, or CP2 or S2 cross S2 with the swap ambiguity, then we know by Gromov that the mapping class group is trivial, meaning that Symp is anyway just Symp 0. And because in these targets there is no H1, this is anyway hum, and then there is no difference, right? Okay. But in high dimensions, we don't know anything about the mapping class group, and then these relations may be indeed heavily different, but nothing is known. There is no result in dimension 6. But there is an observation told us by Yasser Eliashberg, and once you observe it, you can also really prove it. If the domain is a polydisk, then the characteristic foliation on the boundary is a kind of on the flats, very simple. And then since the boundary is not smooth, it's blocking. And this leads to the fact that the difference between the roughest and the second roughest relation is only up to a perturbation, up to a permutation of the coordinate planes. So in dimension 4, there would only be a 2-to-1 ambiguity here. So it means that if the domain is a polydisk, then any self-map can be isotoped to the identity, maybe after composing with a coordinate permutation Z1, Z2. And it is really just because the map is defined up on the boundary, and therefore the characteristic foliation must be preserved. And this gives you much rigidity because the map cannot, it must fix the singular boundary, and then this gives you enough rigidity. So for such special domains, these two relations are actually up to a finite indeterminacy the same, right?
IM is the third.
IM is the roughest one. Just the images are the same. And I say that when you embed a polydisk into anything, and you ask whether the images are the same or the maps are the same up to a symplectomorphism of ambient space, the difference of these two relations is only up to at most n factorial, because you can up to precomposing the polydisk with a coordinate perturbation, you can correct inside of the target polydisk the map.
I see. So you're saying that number 2 and number 3 are equivalent.
Are very close, up to coordinate perturbation, permutation.
Okay. So now you could, I don't know if this is a good idea or not, but you could add a fourth relation where you send one embedding to the other, the homeomorphism.
That's for you.
So then you could, since we know homeomorphisms preserve characteristic foliation.
Understand, could be fixing here. So this remark is a bit special. What we do applies to also other domains than cubes, but it's good to fix cubes as a domain or polydisks. But it's a good point. Our maps are C infinity or C1, but not less. Okay. But good point, because this argument indicates that such a rigidity could be used to say that it's of the same order of complexity for homeomorphisms or
right, because I mean, presumably if you add two homeomorphisms, since there are no homomorphisms, different morphisms, I think they are separate.
Understand.
Presumably if they're not equivalent, they could potentially become equivalent.
Right. I will not hurt. I will not. It's for you. Okay. So now I briefly say what was known about this question, because there is a kind of a very clear picture if the domain and the target has a certain type of form. So the first result in this direction is certainly the one of Duse-McDuff that says that the space of symplectic embeddings of a closed four-ball into a somewhat larger open four-ball is connected. And it's known in dimension 4. And it's unknown in dimension 6, which is a disaster, as Emmanuel Giroux agrees with me, and I think some other people agree. We do not know whether the space of symplectic embeddings of a closed 6-ball into a larger 6-ball is connected or not. And it's a kind of a sad story. But okay, so this can be pushed Namely, it goes like this. If you take a toric domain, right, the ball looks like this. But if you take a toric domain that looks like this, it's sometimes called concave and sometimes convex, and I'm always confused. But embedding of something like this toric domain into something like the other way around, such an embedding space, if not empty, is connected. And this is an extension of McDuff's result that she proved also for ellipsoids to any such kind of embedding problems. And it's key that this is, let's say, concave and this is convex, because otherwise it's wrong. I'll come to it. So the tools here are, first, well, of such a thing you can think of a collection of balls for some reason. So let's think of a ball. And embeddings of balls in all dimensions are strongly related to a surgery, to blow up. And blow up is really related to balls, not to something like cubes. This is why balls are particularly well understood and why such a connectivity result is known, even though only in dimension 4, because in the proof you also need 4-dimensional things like understanding of holomorphic curves and the inflation method of Lalonde-McDuff that is efficient only in dimension 4. Okay, so this is known. And these tools are specific to domain a ball and dimension 4. And I will speak about cubes also in dimension 4, but this completely breaks down. We will prove that infinitely many components. Okay, another example is, of course, even before Crowell's camel theorem. And it's illustrative for several things, so maybe I better make a picture. So you have this, it's about this picture. You have this situation, you take R4, take out an R3, glue back a 3 ball. This is the target manifold. And you take a ball on the left and the ball on the right, and you take the ball bigger than the hole here. You cannot move through in all dimensions. I think in high dimensions, the first proof is by Claude. Crowell's proof is by filling by holomorphic disks, and this is very 4-dimensional. And actually, I think David Perret then reproved this by using Lagrangian tori, and this idea will come up in what I say later. It's kind of a very nice link between, that appeared there probably first time, between Lagrangian rigidity and symplectic embedding rigidity in this setting. Okay, so here is an important remark. It's true in dimension 4 at least, because you can always exhaust by something star-shaped here and then use Crowell's theorem. It's true that there is no compactly supported symplectomorphism of camel space that maps this ball to this ball. But of course, there is a symplectomorphism, namely swapping left to right. So here, compact support is crucial for the statement, right? So these differences in the relations are used. Okay. Then a somewhat later result that is quite fine is you take this simple situation, you take as a target an open cube. And for me, cubes are always open disk cross open disk. Of course, if this is open, this is symplectomorphic to 0 cross interval open to the 4. But if in the domains, I will take closed things, and there I insist that I have a closed disk cross a closed disk and not a closed cube. It's different. Characteristic foliation is different. Okay, so this problem, you take a polydisk and you are a bit careful about the sizes. You want that the sum of the sizes is more than the one of the target, but each of them is of course less, like this reddish part. You take this identity embedding and you also take the swap or the polydisk BA. You cannot move this one to this one inside of this open cube. It was done by Flöchow-Wysotsky as a first application of symplectic homology for subsets of R4. And you understand that if you would allow for a global symplectomorphism, you could do again by swapping. So compact support is important here. Right. And some more results are found by Richard Hind and Gut Ascher and Georgios, that is here. And they are very nice results, and each time they find 2 different things. And sometimes they use, in fact, Lagrangian tori, so this idea is not new. Maybe I briefly say something here. So these also prove the following thing. They take a ball inside of a polydisk, and then they look at a somewhat different domain. So they take something that is slightly more than a ball and looks like this, but it could be C infinity closed. And here is one, and then they take a scaling of that. And you have to be careful with the scaling. It should be a number between 1 and 2 and not everything work. Think of 1.4. So then they look at this domain here, this is my K, and ask about different embeddings into this stretch domain, and lambda is say 1.4. And then, of course, you have the identity, right? But they proved that there is one other one that is not, even not globally symplectomorphic. Here it's even globally okay, which is a bit stronger. And the proof is very interesting, and it goes through, okay, I briefly say, you take an ellipsoid, that is, you take a suitable ellipsoid that looks something like this, that is a bit bigger, that contains the first domain. And then when it's suitably done by ECH theory, you know that this green ellipsoid actually embeds into the bigger one. But you don't see this embedding because you kind of cut into balls naively and then use inflation. And then you never see an embedding. So this embedding, and then you prove with symplectic homology that this embedding is actually non-standard. It's not isotopic when restricted to K to the identity, which is the whole work. But the outcome is that you have two, but the second one you can't see. So my embeddings, you will see, you can see them. Okay, but this is I like it very much because it means that McDuff's theorem, that her theorem would say that embeddings of the ball into such a red domain like K, if it exists, are connected. But if you go C infinity close away into this convex world, it breaks. So it's very fragile, this statement. Okay, good. Are there questions? So this was kind of summary of background. Good, so I want to formulate results. To fix ideas, I started in dimension 4, but everything trivially extends by taking products later, and also by now extends to things like 6 and higher balls and target spaces like balls and CPN, but it's not written. So to fix the ideas, we take cubes, and that more is possible, you will immediately see from the proof when I come to it. And I take first as the target manifold a ball or a CP2, as you like. And I fix sizes so that numbers are reasonable. I take them of size 3. So the symplectic form on CP1 here is area of 3. It's here the natural choice. So I give you now a sequence of numbers. They are related to the Fibonacci numbers, like in the staircase. So you take all the Fibonacci numbers, you take each second entry, the odd placed entries, and then from these Gn, you form this sequence of numbers that go exponentially fast to 0, but are positive. And then I claim that, so you form these numbers, a sequence of numbers that go to 0. And then I look at embeddings of cubes of this size. And this size is between 1 and 1 plus Sn. And I claim that there are at least n plus 1 different non-equivalent in the sense of image relation of these cubes of size A into this ball of size 3. Okay, I will come to the picture more precisely. And maybe much easier to remember is that if you take the limit, so if you take a 1 cube and you embed into the 3 ball or the CP2 of size 3, then you have infinitely many. So I'm not sure they are all, but you have then infinitely many. Okay. Fine. So I will do the proof quite slowly, and in the proof you will see that you can see these embeddings. They are explicit on a set of measure as large as you like, and some people even say everywhere, like for instance Vagal Gunesh says that, but I don't quite understand. Okay, so the main idea is indeed this what already in David Terre's early paper was done, and then also in some of the other papers like the one of Georgios and also Richard Hine used that. So we want to use exotic Lagrangian tori to find exotic embeddings, which is maybe not so surprising, but it has not been systematically used. So you see, I have to write a book, and they wanted more material, and I didn't know what to do because I didn't want to become technical. So I know what I want to add, namely this link from Lagrangian rigidity to embedding rigidity, which was kind of explored partly, but now we have these sequences. Okay, so this idea again occurred earlier, and the idea that I will use occurred actually independently to Yuri Cheganov and Gregory Michalkin, and we systematize it here together with Grisha and Joy Pendel. And indeed, even for this exotic torus in the four-ball, it was before used to find one more embedding by Güth and Asche. Okay, but let me just tell now how the proof goes. So the key thing is to use these exotic tori of Vienna. And okay, it goes like this. I briefly recall you what these almost toric vibrations are. So maybe this is a bit boring. I don't know. Probably half of you knows them well and half not. So I will sketch it. And if there is time or at dinner, I can say more. I will not be very precise. It takes a little bit of time to digest it fully. But it's really a beautiful thing. So you know what a toric vibration is. Here, everything is easy. It's the moment map picture, and your symplectic manifold is just beautifully decomposed into tori almost everywhere. And then there may be some circles at the boundary, and then in dimension 4, and then there may also be points, and you should think of them as subtori, right? Where kind of the torus action degenerates at some places. And of course, in higher dimensions, you may also have TNs and TN minus 1s and so on, strata, right? And in CPN, in CP2, it looks very similar. You have here points, and then you have over boundary points, you have circles, and in the interior, you have tori. And well, I mean, you understand, like, right, R2, you just think of a point and circle and circle and circle, and then the moment map image will just be such an array. And here you have a circle, and here a circle, and here a point, and this reflects this. And here is just a product situation, and here, for most part, is also just a product. So, okay, toric vibrations are nice, but they are a bit special. And now, somewhat strangely, you make them verse, and you change a beautiful torus vibration into a verse one, in an almost toric one, but then you capitalize from that very much. So almost toric vibrations is the following. You make them more general. And in integrable systems, you can go, people go much further. And the key here is to go only the first step further. So you only allow for the next bad singularity, namely croissant. So pinch tori. And they come up very, very naturally dynamical systems. So in this classification result by the Russian school, of course, they were there for 60 years. And they also come up in Lefschetz vibrations as the singular fibers. And they actually, if I have time at the end, I will say that. So they were detected by D'Oystermaat when he studied the spherical pendulum, because the moment map image of the spherical pendulum, here is momentum and here is energy. And then you have on the boundary, you have S1s, and here you have a point, and here you have tori. You have everywhere tori, but here at the center, you have a pinch torus. And it is exactly the planar motion that goes all the way up asymptotically in infinite time, plus this one point that is unstable, which is this special point. And it comes in an S1 symmetry. And D'Oystermaat already understood what this special point is. And he also understood that the monotony around is non-trivial. And this is exactly what happens here. So you allow for one more singularity in the vibrations, namely these ones, but only discretely, okay? And they come up really totally natural. You can write down integral systems that have them. They can also be multiple pinchings, but I don't want them. Okay, so Sung, and sorry for the first name, I don't know how to say it, Nguyen Tien Sung and Margaret Symington understood that you can change. This is the ball, right? This is the open four ball. And this is a strange way to see the open four ball. And these are symplectomorphic. And this here is an almost toric vibration. And it is a schema for something. It's more like symbolic. It means over the whole blue things, you have circles. Here is a circle, and here is a circle, and here also is a circle. So you have actually made this singularity better, but you have paid a lot for it. Here you have a singular torus of this kind, and in addition, this dotted line indicates that if you take a little circle and compare what happens to the torus here, you have monodromy. And the monodromy map looks like this in suitable basis. And this is just the vanishing cycle. So when you take nearby torus, it's the circle that would vanish when you identify with the pinched torus. And this one is the other direction. So this guy nearby is treated by like something like the interest. So this is a non-trivial, it's not just a trivial vibration together with a bad fiber. There is monodromy. This is very important for the sequel. And the key thing is that they are really symplectomorphic. They're not just diffeomorphic. And if I have time, I can explain this. This is really, it can be explained by dynamical systems, or it can be explained by Handelsler, by a surgery, but this is very classical. Okay, so what we do now, we change our good toric vibrations of CP2 into worse ones, because then we can put different tori and therefore different cubes. So let's do that. We take CP2 and you can repeat. So here is the usual torus vibration, a good one, but we replace it totally locally. We only do something here very locally. And this infinity, only in a little ball, we do this, what is called nodal slide, and change it to this vibration, which is worse. And then you go on. So you may be happy with this, but for some reason we push and push and push and push this bad fiber almost to the end, but not quite. So let's stop here, but near to the other boundary. And then, well, and then you change the picture. So you do, okay. You do now a coordinate change. And this was done by Renato Vianna, and it's extremely useful in this setting. So this vibration is not what you want to see. Now you see, over here, here it's special because when I take here a little, here I have monodromy. So what Renato does is he takes this part and he shears this part of the vibration. Here it's again visible, this triangle. He shears it to the, okay, sorry. I should go this way. So this is fine. And now I go further here to this picture. And now I will just do something like a coordinate change. So Renato takes this triangle and treats it with a SL2Z map, maybe something like maybe this, I've forgotten. But it's just the inverse transpose of the monodromy because you want to treat the fiber. Maybe not, it's just something like this. So you move the green triangle down to this green triangle. Over here, you do exactly nothing. And what happens is, the monodromy is now not over this part, but over the other part, because you have undone the monodromy, right? It's really just a coordinate change. But it's much better to work in this picture. The point is that when you look at integral angles, this one is still 1, and this one is also 1. It means I take determinant of integral unit vectors along the edges. And then you see that this vibration here is actually really this one. It is totally standard, only it has a strange croissant torus in the middle. Okay, so after these adaptations, we have changed the toric vibration into an almost toric vibration that contains now, you should look here. Okay, I go to the next slide. I messed it up. So we have arrived here, and since the integral angle is here 1, and here also 1, this is really symplectomorphic by, again, SL2Z in the base and just transpose inverse in the fiber to this 90-degree triangle. So I want to think about my new almost toric vibration as this triangle with certain sizes. Okay? So this was used to construct difficult symplectic embeddings, and of course, Renato Vianna used it to find exotic Lagrangian tori, namely the old torus is now still here, but it's not, it's a different torus. And he distinguished them, and now we use them to find cubes. Okay, this I will now prove that in this new vibration, I find one more cube that I have not seen before, but you could, this nodal trait and no, this nodal slide plus this second operation, coordinate change, that is called trading the node, you can of course iterate, and then you get infinitely many. So let me prove that the standard cube in CP3, in CP2 of size 3 is different to the one that I just put by identity into the new almost toric vibration of CP2. You see, this is really a new way to see CP2, but it's still the usual symplectic CP2. So into this somewhat strangely written space, I put the standard cube, just the way, just by identity, relative to this new almost toric vibration. So I know that this new thing describes CP2. So now I unfortunately must take A quite small because I have to fit my cube in. But the key is that for any number A bigger than 1, I do have this special torus here because he is at 1, 1. He does not move. Okay? So I have this identity embedding here, and I also have a new embedding, namely the identification of this new way to see CP2, just restricted to the standard cube, this red thing. This also gives an embedding. If A is not too large, should be less than 6/5. Here I need only less than 3/2. And I claim that these two embeddings are different in this strongest sense, in this im sense, in this weakest sense. Okay. Okay, proof is just because the tori are different. So I claim they are different, or assume not. Assume we do have a symplectomorphism of the projective plane that maps the first standard embedding to the new embedding as a set. Okay? So using Yasha's lemma, I know that I found not only a relation between sets, but a relation between maps. Namely, after precomposition with sigma, this identity can be corrected by an ambient symplectomorphism to this strange embedding of the cube, right? But now I restrict all this to the central torus. So you see, sigma actually fixes the central torus. So I can forget about it. Identity 2. So after that, I found that the usual Clifford torus is symplectically identified with this strange torus. But this is not true because this Viana torus is not symplectomorphic, as Renato showed by using count of holomorphic disks. I will come to how they are distinguished. This is known to be not so by Renato, and also Galkin and Michalkin had a somewhat different approach to this. And I will, if I have time, say it by an easier method, by versatile deformations, why these tori are different. So this finished this proof. There you see, there is not much going on. We just use these tori. We are a bit lucky that they are even sigma invariant because they are Clifford in this picture. And then we just enumerate. Questions? Okay, so now you can go on, right? We have these strange vibration, almost toric vibration, and then you can go on. You can shear again, and then shear again, and go on and go on. So you should always do it in such a way that one corner has still integral angle 1. The integral determinant should be 1, otherwise I cannot place a cube. So therefore, only some of them are useful. So now you do the numerics, and you get this sequence, Sn that I wrote down, and you exactly follow to this, what we now call maybe Fibonacci or Markov triangles, and you could easily compute their sizes. You go on with these mutations. This composition is called mutation, and then you compute how big the cube can be, and you find exactly these numbers. So I'm a bit too much in love with numbers. Sorry. Probably it's boring for you. What happened here?
Sorry, Felix, a small question.
Yes.
Yes, in the example you gave, that torus at 1, 1 is just the Chekhov torus, right? It's not yet one of Vienna's weirder torus.
First one is the Chekhov torus, the little argument to see. Of course, I use Renato's description, but I insist on the iterations, right? I want to get infinitely many, so I use Renato's description.
Okay, thank you.
This is.
Excuse me, may I ask you a question, Felix? So you take the cube. I mean, your domain is the toric domain associated to this square, but now with different toric with this different toric description.
Well, thanks for the picture for the question.
So is it clear that it is a bidisk or?
This red thing is a polydisk, yeah? It's a standard moment map image of the polycube, right? Of the cube.
So is it so? Maybe this I didn't understand. So
you see
you have a different toric action, right?
The almost toric vibration is standard away from this part. Away from that, it is totally standard. Therefore, I can put the standard toric vibration of the cube into this almost toric vibration. The picture before was something like this. When you iterate, you will actually get more and more of these crosses and these bad pinched tori, but you can locate them as close to these corners as you like. And in the complement, I still have a total usual toric vibration. And I put the cube always here so that this almostness, this non-standardness is just not seen by this part of the embedding, by the cube embedding.
Okay, thank you.
So it's also a good point to say you can, of course, embed many other things. Anything that is something like any set that you see, I mean, Renato says the two tori are not equivalent. I take any open set that contains these tori and I get non-equivalent embeddings. It's really super easy. Okay.
So sorry, is it clarification? Could you clarify where was it down torus, or where was it the boundary?
No. They are these tori, the 0.11. This torus is the Vienna torus because he sits in a different vibration.
But this is in the interior of the.
In the red picture, I work now with A strictly bigger than 1, but I could take the closed cube. By definition, it extends a little bit, and this set contains it needs a little bit care to go to the limit, but it's fine.
But
yeah.
But the argument is that's for it can't live on the boundaries.
What I say is it is for the open case where A is strictly bigger than 1. But now take 1, applied by definition, I have a map that extends to a little neighborhood. I apply there, and the cubes of size 1 are all mutually inequivalent, and they are infinitely many. Thanks. Other questions? So hopefully I have time to say how this can be done very elementary by versal deformations. But maybe I do now. Okay, so up to now, we only checked how to go to CP2. Now I wish to say that they're actually different in the ball. So here I need my assumption that my embeddings have compact support. Because I take now 2 embeddings into the ball, since I have compact support, I can extend to CP2, then apply this and conclude. But for this, I must check that in these previous vibrations, I can really avoid a CP1 at infinity. And this is not totally obvious. So for these embeddings, it was very nicely done in recent work by Roger Casals and Renato Vianna. For embeddings of cubes into S2 cross S2 or CP2, you could use next stretching to prove that any symplectic embeddings of cubes are movable away in a Hamiltonian way from a CP1 at infinity by next stretch. But for somewhat different domains, this would not work. So there is actually something more generally true. And then this leads to the fact that you also have the result if you want to embed into a ball. Okay. have to take care that these embeddings actually don't touch a CP1 at infinity, but this is fine. Okay, so, okay, I go here a bit, what do I have, 15 minutes? Or maybe I go a bit fast here. 50?
You started 50 minutes.
Okay, good. I go a bit fast. I like these numbers so much. And I want to embed into a cube into a fixed cube. The sizes are now different. And here's something I like happens. You get much more, and the numbers get much more interesting. So here you get a similar result. You get a sequence of numbers that go to 0, such that if you stay a bit above 1 up to this number, you get n many different. And at 1, here is should be a 2. You get infinitely many embeddings into the cubes of, or the sphere cross the sphere of this size. The advantage is that this sequence does not go exponentially to 0, like the Fibonacci thing, but only quadratically. And the reason is that you now have almost toric vibrations over a rectangle, and then you have more possibilities, and then the size, then you approach the good torus much slower than before. So, yeah, this is just this. It doesn't go exponential, but it goes quadratically. Okay, this sequence before, this Markov sequence, Fibonacci, goes much faster. And the proof is similar, but you see here you start from the usual S2 cross S2, and then you, as already Renato did, you come to this one, and then you get triangles, and then sometimes from triangles, triangles, and then fourgons, and then from fourgons, fourgons or triangles, and then you get a much richer graph, which is probably a tree, but we don't know that. So I'm a bit fast here. So you get this picture. You start with a square, and then this line is what already Renato did, the blue line. He only worked out triangles. They would go exponentially fast to 0, but there are actually other families. You see, there will be many, many fourgons and threegons. Those that have an integral angle 1, only those are useful to us because I must be able to put a cube. So all the white ones I throw away. They are not useful for us. They are useful to find new tori, but not new cubes because I cannot place a cube. But then among the colored ones, there are the super good ones, the red ones, the good ones, the yellow ones, and the bad ones, the green ones. And to enumerate, you see, I conjecture that these are all tori, and from these colored guys, you get all cubes. So in a way, I want to understand them a bit. And this is a kind of a strange story. So there are these triangles, and they are only here, the blue ones. Then there are the good sons. You see the triangle, each triangle here, the blue one, has, well, this one has this very good son. And then typically after 2 generations, the red guy has one good son and one bad son. And good and bad, bless you, Claude, is defined as follows. Good one is if the one cube fits in, but it may not, because the vibration may actually look, if you put it in normal form to get here a 1, may look like this. And then the torus is useless. You cannot use him to get rigidity. So this enumeration, maybe, I don't know, maybe you don't care for it, maybe you only want to have infinitely many at size 1. But we looked a bit at that, and there are some fat ones, and then you get numbers, and the bad ones are useless, and you cannot use them. And the full enumeration looks a bit difficult. But a student from Lyon, Thomas Bugdalche, did much on it. And these fourgons were also used by James Pascalev and Tom Knock to find new tori. Of course, you could try to do that also on 6-gons and 7-gons on Fano, but I don't want to do that. Okay. I maybe say briefly, I'm now a bit fast because I want to say something about the distinction proof. So you can very easily go to higher dimensions by taking products. Taking products with anything monotone, because then in the monotone fact, you just put the Clifford, the central torus, and you repeat that, and the invariants are such that tori are still all distinguished. And then, of course, if you go to products, you get many, many more, right? Because you have so the counting function becomes much better. So this is the same as before, but for when you want to embed cubes or slightly deformed cubes into such monotone products, You can take them closed, or you can take them partially closed, or you can take as, I think this is not so interesting. You understand. From this you can fastly push by taking products. You just take the Clifford torus in the new factor. But what is interesting is that it works for cubes into CPN and also the ball. So I think Renato Viano knows that the idea is you do the same as before, and you take a suspension of the picture. And I think he already knows how to produce now exotic tori. So Grisha Michalkin has a different proof of this, more like with toric, with degenerations and smoothings, that you can also, that this picture of the nodal slides can be suspended, and then you cannot suspend it in one shot. You go to 6 and then to 8 and then to 10, and then you get indeed embeddings into non-products. We looked for this for a while, but I think now it can be said that it works. You can go to any products of CPN, and you get really new examples also in the 6. You get infinitely many islands in pi0 of embeddings of such domains that contain a big enough torus into the 6 balls and the 8 balls and so on. Okay, but maybe I briefly say something about the proof. You know, I'm not so good at J-disks. So Lagrangian tori are classically distinguished by counting J-disk of Maslov 2 with boundary on the Lagrangian, enumerating them. You must take Maslov 2 because otherwise you have compactness problems. And then you try to enumerate them. And the idea goes back to Leonid and Yasha, who found the description of the Chekhanov torus in C2 and distinguished them by counting the disks. And then Renato and also Grisha and Paskalev and Tonkonov use these J-disks. They are, of course, very important because they say something about the potential and they are related to other things, but it is quite difficult. And for instance, this paper is not easy at all. It uses a Fleur theory version. And I want to do it in a very easy way that I briefly want to recall. It goes back to Chekhanov's old idea of versatile deformations. I compute a certain symplectic invariant near my difficult torus to understand that this difficult torus is different from another difficult torus. So these tori are all monotone, and the idea is to look at nearby ones. Okay, you look at nearby tori. You see, you have a torus and you don't understand him, for instance, the Viana torus, and you look at nearby tori, and the invariants you know are not distinguishing this torus. For instance, displacement energy is infinite, always infinite because always non-displaceable. But you look at nearby tori, and the behavior of your invariant at nearby tori will be such that you can distinguish these exotic tori in this way. For instance, you take displacement energy, right? Maybe you know that you have a subset A in a symplectic manifold. You try to displace it by a Hamiltonian isotopy, and you take the Hofer norm of the isotopy, and you take the cheapest one, the one with in Hofer capitalism, so the Hofer norm cheapest Hamiltonian isotopy that displaces the set from itself. Okay, for instance, and this is not easy to prove. For a circle, it's easy to see that the disk of size A needs energy not less than A. But to prove that you cannot do better is actually not easy. But it's known by Helmut. Okay, so the problem is that, for instance, the Clifford torus in CP2 has infinite energy, but the nearby ones not. They all have finite, almost all of them have finite energy. And you should not study this displacement energy on this infinite dimensional space of nearby guys, only nearby up to local Hamiltonian isotopy. And the local space is, of course, by Weinstein parametrized by a little neighborhood of H1. In the center, it's my torus, and nearby, they are really Hamiltonianly, locally Hamiltonianly different. It's important local. Should not on the sphere move globally. Different tori, and since displacement energy is Ham invariant, you go down to this quotient. So from this, you get on this quotient space H1, you get a function germ. It's only defined nearby. You go a Weinstein neighborhood. That maybe at 0 it can be infinite and takes real values. And now if two tori are symplectomorphic, ambiently symplectomorphic, these two then you choose a basis of H1 and immediately find that these two functions on H1 must be linearly related. They should be, if the two tori are the same, should be a relation of this form. The two tori, the energy, okay. On nearby tori, parameterized by H1, I have the energy displacement function given by the torus in question. If the two tori would be symplectically equivalent, then there would be an SL2Z matrix relating the two maps. So, for instance, for CP2, you immediately compute the energy displacement profile. The level lines are given by scales of the boundary, because the energy you need here is given by the distance to the boundary, but the integral geometry distance, the affine distance, this length, and here this length. And for S2 cross S2, here it's this, and here it's this. So it means that the energy, so okay, you just get, it means that E knows the shape of the torus base, of the torus vibration base, right? If I give you a value C like epsilon, and I take the preimage of this level C, I actually know the shape of the torus space. Okay, so I don't want to discuss this. It means that for the torus, for the toric vibration, we have computed it. And the key is that this picture easily propagates under mutations. It's easy to see that if you do the mutation, yeah, nothing happens. This torus will go to this torus and his displacement energy will be the same. It means that just taking scales of the boundary here, when I take scales of boundary here, again, it gives me the displacement energy profile. Yeah, but now it means the following. It means that if two Vienna tori would be the same, it would mean that the basis of the almost toric vibration should be SL2Z related. There should be an element herein that maps one base to the other one. But you very easily see, for instance, in this tree on this Markov, yeah, that the integral angle of the largest one goes monotone strictly up. But the integral angle is an SL2Z invariant, so cannot be, so they're all different. So this means that the tori are all different, and then also that the cubes are all different. And the integral angle is, so when you have such a thing, I just take, in the two-dimensional case, it's just the following. They're all rational, so I take a vector along the side, and it has integral length 1, and I take here a vector of length integral length 1, and then I take the determinant of the 2.
So integral length 1 means that it's an integral vector with
it has
common divisor 1.
Exactly. It has Fi. If you take an SL2Z map that takes this vector to E1, it has length 1. It means this.
And so what's the integral angle again?
The integral angle is the determinant of V1 and okay, of U and V, if this is U, if this is U and this is V. And this is SL2Z invariant. So there are other ways, but it's very convenient to just enumerate the integral angles, and this gives you an invariant for the basis, and then for the torus, and then for the cube. It is, well, I think it's much easier, but of course, I agree that the two disks are very important for other reasons.
Can I ask a question about this picture? So first, don't you need some first say that?
Yeah, thank you very much. So I like this question. I like this question very much. So Joey Brendler observed the following. So how do you prove that the displacement energy of this point is this? So by idea of Dusa and independently Jurij-Chikhanov, you take a probe, namely you restrict the vibration over here, reduce some S1 action, then you in the quotient you have a disk, but you see you have also a disk that is more than twice bigger than inside of this disk. So this circle, this remaining circle, you just move away with area A into the complement, and you can do it because this is longer than this. And then you lift this Hamiltonian isotopy to the total space, and therefore prove that this displacement energy is less or equal than A. Now you would like to prove bigger or equal than A. Now everybody says you need J-disk. Not true, because you can do Del-Sound construction, and it starts at, okay, let's do it. Oh, it's blocked. Okay, I write here. So you do this sound construction for CP2, and for CP2 it goes to C3. If I would take S2 cross S2, I would have to go to C4. What happens under the sound construction to this torus of size AB? Okay. Sorry, I made the mistake, so therefore I take S2 cross S2. Now it will be this integral length, but I take S2 cross S2. It's more informative anyway. So I have here the torus AB. This torus here will lift to the torus A, B, 2 minus A, 2 minus B, namely these. It's how the sound construction goes. So Jean-Claude Sikorev proved in his habilitation thesis that the displacement energy, and this is exactly the Hofer-Zehnder proof for linking and their capacity, is only variational principle, is only linking in loop space, that the displacement energy of such a torus is the smallest entry. But okay, now you have to do the inequality in the right way, and this proves the other inequality. Because when you can displace here, you can displace here. You can again lift. But this time you have not reduced, but you have lifted, and therefore you get exactly the other inequality. So we need for all these toric manifolds, you never need J-disk, but it's a little bit, maybe one should also learn J-disks. But Schoy-Brendel worked this out very nicely. You don't need them. No, you can reduce it to the linking. Thanks for the question.
So this can explain things away from these lines.
Pardon?
This can explain what happens to the tori away from these breaks.
Exactly. This is so. You see, when you now you do this Vienna mutation, here it's the identity, and here it's very explicit. So the whole embedding is explicit up to, in my construction, up to an arbitrary small neighborhood over this line. And some people say up to over, yeah. I think Baral Günish really tried to explain to me that he knows exactly, he thinks like in linear affine geometry that you could, it's really piecewise gluing, but I couldn't figure it out. We have problems with Moser to do it you should do a limiting argument on Moser. Maybe it's not so important. You give me 99% of the volume, and then there we can do it.
But can you, for instance, answer whether the bigger Chicago tori are displaceable?
I have to think about it. Yeah. Your question is not forgotten. I think you can see many. So you may remember that these almost toric vibrations have been used extremely efficiently to find these difficult ellipsoid embeddings by Casals and Vianna in an extremely efficient way. So I think it's very good to know these toric vibrations, and when you have a question in these monotone manifolds, you can maybe see things go very well there. Yeah, thank you very much. It was a real pleasure.
Thank you.
Okay, thank you for the talk. Any questions? Any further questions? Maybe you should take a look at the chat. I think most of those are from an hour ago, but
what is written?
Oh, no. On your iPad.
I cannot. I don't see this. This was the problem why we had it.
Okay.
This table doesn't show the. So maybe you can read them.
I don't understand. I think they're mostly from an hour ago anyway.
I'm sure they are all answered.
Okay, so I can't see the chat either.
So maybe the person that asked can read it.
Actually, can some of the Zoominar organizers take a look at the chat and because we seem to not be able to see the chat.
There's only one remark that has been addressed, so it's good.
It's all good. It's all been addressed.
Yeah.
Great.
Okay. Okay. So if there are no other questions, then let's thank Felix again.
Thank you.
Okay. So thank you very much. This brings us to the end of today's activity.
It was a hard day.
Okay. Have a good weekend, everyone. Thank you. Thank you all for coming.
Goodbye.